If you're building AI applications today, you're probably doing something like this. You let your AI model generate an output, and then your application uses that output, renders it, executes it, searches it. However, if you're doing that in an insecure way, you might be up for bad surprises. Hi, my name is Bernard Wonasek. I'm a cybersecurity consultant working in Vienna, and in this video I'm showing you a hopefully useful way to think about output handling in AI systems. Let's go. First, let's start with the official definition of LLM05, improper output handling. Improper output handling refers specifically to insufficient validation, sanitization, and handling of the outputs generated by large language models before they are passed downstream to other components and systems. Let's break down what this actually means for a typical AI system. Let's say in your AI system, an input is first sent to an LLM, then the LLM generates an output, and then this output is used in your application. For example, let's say you want to build an AI-based calculator. The calculator application gets as an input a user description of what it wants to calculate. Then it uses an LLM to generate Python code out of that. And finally, the code is executed by the AI system and the result is returned to the user. Now, there are different things you could do in your application with the LLM generated output. For example, you could use the AI system to render the LLM generated output, for example, in an existing HTML view. So you could just assign the HTML output to some existing HTML element. Or you could use a function like eval to directly execute the code that is produced by an LLM, or you could also use the LLM generated output inside of a database query. In all of these three cases, the output is directly used and you treat it as if it were generated by a trusted backend API. However, there are different vulnerabilities that can occur in these scenarios. For example, cross-site scripting in the case of in-HTML, remote code execution in the case of eval, and SQL injection in the case of usage in a database query. Why is that the case? Because the bug was never really about the output itself. It's about where the output goes next in your AI system. Every place your app sends it has its own interpreter, something that turns the text into action. If you send it to the HTML page and the browser reads it as HTML, you have a cross-site scripting vulnerability. Send it to a database query and the engine reads it as SQL, that's SQL injection. Send it to eval or shell and the system reads it as code, that's remote code execution. It's basically the same single mistake every time. You took untrusted text and handed it to something that treats it as instructions, not data. The vulnerability just borrows its name from whichever interpreter you feed it to. Now let's go back to the example we mentioned, our AI calculator. We can enter a natural language question like what is 15% of 200, click calculate, and we get a result that is first correct, but also AI generated in that the system was able to generate the mathematical expression to find the right answer. What happens in the background is that the raw code that is returned by the LLM, in this case 200 times 0.15, is handed to an execution engine that treats this as code and executes it. And you get the result, in this case 30. But now let's try to think like an attacker. What if I enter something that is not a mathematical expression, but something like what's the current system's uptime? Well, the LLM still knows how to achieve something like that, right? It can use other packages to find out the uptime, and the resulting code again will be executed by the code interpreter, and the result will be the current system's uptime. However, this is now quite dangerous, of course. Instead of the system's uptime, the attacker could also ask for things like the SSH keys or the user's passwords or something other confidential, right? So the problem is not that the engine is so generic. That's of course the intended thing. However, the problem is that the output of this engine is just blindly executed. There is no validation step at all. Now let's quickly look under the hood and see how such an implementation could look like
behind the scenes. In this case, we're using ban.serve to serve this really small demo application on port 3000, and it's basically just taking the param from the user, that is the question, and it's then sending that question to an LLM, taking the output of that LLM, and then in the highlighted portion of the code, it's using eval to just run the code that was generated by the LLM, which is of course quite unsafe. We don't know what kind of code the LLM would return here, and then returns the result of that evaluated code back to the user. As you can see, that's about as dangerous as we just demonstrated. By the way, while this AI-based calculator was of course a demo application generated specifically for demonstrating this vulnerability, this is by far nothing very exotic. In fact, the NVIDIA developer blog is describing similar scenarios as still actively exploited, citing, for example, the case of active content rendering of LLM outputs as part of a markdown engine. So while this seems far-fetched, this is a quite well-known and also still occurring kind of attack. One very common question at this point is, how is this different from prompt injection? Well, we'll get there in a separate video, but basically prompt injection might be one of the reasons why the LLM gives you a bad output in the first place, right? Prompt injection would be something affecting the input of the LLM, while other techniques such as poisoning could affect the LLM itself directly. In both cases, it's important to understand those are mechanisms to influence how the LLM behaves, but it doesn't really matter how the output becomes malicious. The fact is, this could also be an inert property of the LLM itself. It could happen by chance. It could happen because the LLM itself was just trained to do so. There are different reasons, prompt injection being one of them. However, this doesn't change the fact that you have to protect your AI system at the level of the output encoding. And the good thing is, while for prompt injection there currently is no technical defense, for output encoding, gladly there is. And let's look now into some of the mitigations we can use to defend against this kind of attack. First, never trust the LLM's output. That's the whole mindset in one line. The model's output is untrusted. Treat every token it gives you exactly like text a stranger typed into a form. It's functionally what it is. The moment you think it's your own model, so it's fine, you've already lost. Second, context-aware encoding. You have to encode the output depending on where it's headed. If you want to render it in an HTML page, you have to HTML encode it. If you want to use it as part of a SQL query, you have to use parameterized queries for that. Same rule as the attack, the sink that decides the vulnerability also decides the fix. 3, least privilege. If you can change the privileges that are used to execute the code, you can shrink the blast radius. So the model and the code that runs its output should have the least access that still works. For example, if you only do read-only database queries, you just need a read-only database user. And finally, as always in good systems design, use defense in depth. Assume that you still miss some of the cases that result in vulnerabilities like that and build your system around it. For example, build a sandbox to execute the code, use a strong content security policy to catch cross-site scripting your encoding is missing, and add logging, of course, to at least be able to monitor after the fact what was happening that caused the attacker to succeed.
All right, in summary, we have learned that AI models are acting similar to very fast, very brilliant, and completely untrustworthy users. Treat their output accordingly. Make sure to build your defenses, apply the mitigations we talked about, and you will be safe from a whole class of bugs in your AI systems. See you in the next one. Have a good day and bye-bye.